All right. So we're going to start off the class with a pop quiz. Nothing beats pop quizzes besides not having quizzes at all. Right, Odessa? All right. So on your piece of paper, you need to draw these four pictures. Then you're going to tell me which one would have the faster rate. All right. And then you need to tell me why. For each of the four. These are the four factors that affect the reaction rate. You're going to circle which reaction has the, or which picture of each pair has the faster rate, and then you're going to tell me why. All right, ready to go. 5 minutes max. This is it. So you can use your whole paper for the picture. I'll pause the record. Okay. So most of you said the following, just glancing through. You circled this one and said because it's more concentrated. Well, that's kind of right. Most of you circled that one and you said because it's hotter. Well, that's right. But that's not really answering the question. So let's make sure we have the key words that you need to pass your test. The more concentrated, the faster the rate, because you have more collisions. More stuff, more collisions. Odessa, halfway through, she was the only person that used the word collisions. She put more concentrations equals more collisions. We need two things for a reaction to happen, a collision and energy. So the Y should replace, or sorry, should have at least one of those two things in the explanation. So more stuff, more collisions. Hot, I gotta change. Woo. This one's, no, depending on the state of my facial hair, it's like a little Velcro and it moves it. And I'm at a time in the week where it moves it down and I inhale it. And then it makes me want to choke. I don't know. First one props. Okay, here we go. So tell your partner quick, this one, which we know it's hot. That's not hard. But now why use these terms? All right, it has more energy. But on the test, you should use the word or see the word frequency. Frequency and energy of collisions increases. That's the exact answer from the test. So temperature, you don't say hotter reacts faster because it's hotter. You say it reacts faster because the frequency and energy of the collisions increases. Okay. Particle size. The key word here, and I didn't even look for, I only read this one for everybody. More what? Do you remember the key word we're looking for on particle size? Starts with the S. Surface area. Turn to page 4. I'm pretty concerned. Page 4. Look at the third thing at the top of page 4. Does it not use the word surface area? Oh, we didn't do that. Okay, that makes me feel better then, because I would have thought for sure we would know that by the SUR. Okay, so Odessa says this is half my fault. Page 4, there was 1, 2, 3 things at the top, right? Number 1 we did. All right, number 2, here's the exact quote. It's this thing right here. The frequency and energy of collisions increases. You got to know that. All right, then For the third one, it was where we made it a powder instead of a chunk. More surface area means more collisions. More surface area, there's more places for the reactants to collide. So on your exam, look for these keywords: frequency and surface area. That will give you 2/3 of the answer. And then the higher the concentration, the more stuff, the more collisions. Just think of a full parking lot. Much more likely to have a collision here than here. All right, then yesterday we talked about a catalyst. All right, a catalyst, which one is faster? The one with a catalyst, right? And the reason why on this one is it lowers the energy required. To start the reaction. So if I don't have to climb as big a hill, I can get over the hill faster. You okay with that? The catalyst lowers the hill for me. It's like a tunnel. You ever play that game with like the hills and the bird? And like you ramp up the hills. And then there's the one hill with like the tunnel. And if you time it right, you win every time. Anyone play that? I love Tiny Birds. That's what it was called. You never played that game? Yeah, a lot of games like that. If you could time it, usually like your jump had to be from here, and you time it just right, you'd be like, oh, boom, game over. You leave all the other birds behind because you get it. I'm just talking about Tiny Birds, one of my favorite apps of all time. We good? Okay, so what does this have to do with chemistry and what I was just talking about? A catalyst. That would be like the tunnel. Instead of having to go over the top, you go through the tunnel, you get there faster. That's all. You okay with that, Blake? I'm sure you're okay with it. Okay, I think we're on page 5, maybe 6. 5. All right. The rest of the lab book. What? Which way did it go? Okay. You know, there's also a screen right behind your head. Okay. Well, okay. Like a secret tunnel through the mountain? No one's going to start singing that. No. Someone in my religious boundary was in a car accident on the freeway. It's not bueno. Okay. Which way did it go? Here we go. Page 5, right? Is that what I said? Okay. Did I already say the rest of the lab book goes by pretty quick? Okay, it goes by pretty quick. So today's Wednesday. We could test Monday, but we'll make it Tuesday. Sound good? Test on Tuesday. What's that? Okay, so probably Wednesday then. Monday tests, everyone sucks at. President's Day, I just forgot about it. All right. All right, page 5. My friends, this concept is not hard at all. Just trust me. There might be a lot of words, but I promise in the long run, this is one of the easiest things ever. So far, we've only looked at reactions that went directly from reactants to products. This is not usually the case. So this is all I'm really going to change. Please look at the screen. I have A, and we've been putting an arrow, and I've said it made B. All right, now I'm going to trick you up here. From now on, we're going to say it could go both directions. Whoa. I could have B react to form A. All right, this actually is a very common thing. A lot of reactions, they go one way, but a lot of them also go both. All right, here we go. In nature, there are many instances when as the products of a reaction are formed, they may break apart or join together to form the original reactants again. Yeah, it is kind of cool. So this is obviously the same thing from last year, but I just wrote it different. We had A plus B makes AB. Or we could have AB break apart to form A plus B again. What's that? All right, so this is a decomposition. What would the original have been? Yeah, you don't survive in a house with that many kids being dumb, right? You learn quick. All right, this direction would be composition. So things can break apart or reform. They do it all the time. I have a thing on my desk. I'll show you in a minute. When this happens, we call it a reversible reaction. It's one we can reverse. It can be represented with the following symbolism. Again, it's just a two-headed arrow. That's the only difference. Instead of just pointing that way, we're going to say it could go either direction. Really simple. Okay. I should go back real quick. Oh, no, we're not there. The reaction is really two reactions. The reaction written from left to right is called the forward reaction. So we have all year long been studying what we call the forward reaction. It's when our reactants do whatever they do to form products. That's forward. Any guesses what we're going to call the other one then? The reverse reaction. The reaction written from right to left is the reverse reaction. In a reversible reaction, both the forward and the reverse reactions occur at the same time. This is a matching term. That was not a very good line. All right. You have to write it, like, write down paper, all you do is you put a double arrow. And that's literally it. That's why it's not much harder. We're just saying it could go that way or it could go that way. All right, now you do need to know this, the definition of a reversible reaction. You do need to know that a forward reaction is when we go reactants to products, and the reverse is when we go from products to reactants. All right, short little video.
Reversible reactions. When we fry an egg, it is impossible to unfry it. A lot of reactions work in the same way. Once it is done, it is irreversible. In this lesson, we will learn about reversible reactions. When we In this lesson, we will learn about reversible reactions. When we fry an egg, it is impossible to unfry it. A lot of reactions work in the same way. Once it is done, it is irreversible. A good example is the combustion of magnesium to form magnesium oxide. Reversible reactions are reactions where formed products can revert or go back to their original reactants. Since the reaction can proceed in either direction, we use this reaction arrow to represent reversibility. An example of a reversible reaction is the thermal decomposition of ammonium chloride to form ammonia and hydrogen chloride. Place ammonium chloride in a boiling tube and heat using a Bunsen burner. Ensure that this is conducted in a fume cupboard, as ammonia and hydrogen chloride are both corrosive gases. If we hold red litmus paper at the mouth of the boiling tube, it turns blue, which confirms the presence of ammonia. Blue litmus paper turns red, which confirms the presence of hydrogen chloride. Remove the boiling tube from the heat and let cool. Have a look near the mouth of the boiling tube. You will see that there are white crystals. These are ammonium chloride crystals. So what has happened here? Ammonium chloride has thermally decomposed to ammonia and hydrogen chloride. The formed ammonia and hydrogen chloride have reacted to produce ammonium chloride. Therefore, this is a reversible reaction. Why is the thermal decomposition of ammonium chloride sometimes incorrectly called a sublimation reaction? Please pause the lesson to think about this and resume when you.
Oh, I should talk with my mic on. Okay, I heated this up this morning. It's the exact same thing she talked about. Let me turn the lights on real quick. All right. So I took ammonium chloride and I put it here in the bottom, and it's just a powder. And then I heated it. Now, this test tube was clear. It was clean before I started it. All right, so I heated it. Some vapors started to come out of the test tube, and then I took the test tube out of the heat, and then you can see this white stuff all around. Any guesses what the white stuff all around is? It's the same stuff. It's the same stuff, because as soon as I removed the heat, the reaction started to go right back the other direction and reformed ammonium chloride on the wall. 1 second. So this powder and these white crystals stuck on the side are the same thing. It separated, then I removed the heat, and it came right back together right there. Go ahead. Definitely. I did it in that fume hood, or as this lady calls it, a fume cupboard, which sounds so much cooler. But anyway, that's the exact idea that we can see represented in that chemical equation. All right. Now, not every reaction is this way. When I burned the magnesium and it cooled off, it didn't reform into the shiny metal, right? It was done. That gave off so much energy, there was no way to just reverse that easily. Okay. Let's come back here. All right. Now, this is sort of tricky here. Well, it's coming up in a second. When the forward and reverse reactions are taking place at the same rate, there is no net change in the actual amounts of the components of the system. Actually, I had this, I was very comfortable here. All right. So what this is saying is if I earn $5 and I spend $5, what's the total change in my bank account? 0. In our reversible reactions, the forward and reverse are happening at the same time. If they also happen at the same rate, there's really no change. Okay, different things have reacted both directions, but the overall change of the system is 0. It's a really important part of chemistry. We don't talk about it that much in normal chem, but AP, they have 3 chapters of this. It's like a month and a half. All right. The reaction has reached a chemical equilibrium. This is another matching term. How was it? All right, good. When the forward, oh boy, and reverse reactions are taking place at the same rate. Same rate. All right, now, this term is super tricky. Equilibrium and reversible reaction, if I come back, they're almost the exact same phrase. So you got to be really careful here. Reversible reaction says both the forward and the reverse reactions occur at the same time. Does anyone remember the difference then for equilibrium? Same rate. Time and rate are a different thing. Now they're related to each other, but the key word is equilibrium is when things are changing at the same rate. All right. Has anyone ever tried to make a pile of sand? It doesn't work all the time. How come? Okay, it's not wet. That's true. So sand, it's actually math, but I won't super nerd you out. Depending on the wetness of the sand, sand has a certain angle that you can make the pile, but you cannot ever make the angle higher. So what? Just trust me. If I pour sand on the top of this pile, I'm going to pour it on top, but where's it going to go? It's going to go down here, right? Okay, so it gets wider, then I can get it taller, but this angle will never, ever, depending on its wetness, of course, it's the same angle every single time. You are good. You understand basic science, you just don't like doing basic science, pretty much. Okay, so if you think about this, I both added and it subtracted about the same amount. So the height really didn't go anywhere. Now, you know what's super cool? You ever tried to dig a hole in the sand? Same angle. Isn't that annoying? Digging a hole in the sand is the worst thing you can possibly do, because you're going to take your shovel and you're going to get something right here and you're going to scoop it out and throw it that way. And what's going to happen? More is going to fall right back in. So the only way to get deeper is to do what? Make it wider, because the angle here will always be the same. So I know it's kind of weird, but the sand pile and a sand hole, they always have the same structure. I didn't really mean to try this, but let's figure it out here. Not bad. All right. So this is sort of an example of something at equilibrium. I add, but it moves away. So there's no real net change unless I make it wider. So I have to change a different condition. All right. Now, this is a super duper misunderstood thing here. I draw these once in a while. What do I call these? My red flags. Red flags. That means kids get this wrong a lot. The fact that the rates of forward and reverse reactions are the same in a chemical equilibrium does not mean that the amounts of the components on both sides of the chemical equation are the same. Okay, so what on earth does that mean? Well, I could go back to my sand here in a second. So fill that out. And then I'm going to go back here. So let me get this back the right way. If I were to dump this sand on and I both added and it went away at the same time, that doesn't mean I have the same amount of sand in my pile as I do my beach. There's way more sand on the whole beach, right? All right. So we're going to say that the change is equal, but the amounts do not have to be even remotely equal. You know that? So like there's a lot of examples. Just because earn money from the school district and I spend money doesn't mean that I have the same money as the school district. No. School district's the largest employer in our county. It has a lot of money, yes. You never would think about it, but it's by far. Yeah, you got host. I would be mad. Well, you can go play on it right now. Well, you can't when you're healed. All right. We will do a lab to emphasize this. The amounts are not the same, just the rates are the same. All right. So, well, I can do this demo right now. I forgot. This demo is not, yeah, I'll do a demo right now. There's no real chemicals involved, but it's really good at talking about this. You guys having fun? All right, good. All right. This was made by someone just like you, Blake. Genius? Yep. Not a science lover, but a genius. And he was handsome. Just like you. Right? Okay. All right. Was that loud when this fell? Could you hear that? Oh. Oh, you can't even see my cute smile. I only do that because these are plastic. I gotta double tap or multitask here. Oh, that one fills faster than I'm pouring. All right. Here we go. Smarties and water. That is finally a time you kids are allowed to use the word dissolves. They dissolve. Then it dissolves faster. Feel like we covered that. Okay, here we go. I'm going to add water over here. These are connected with a hose. It's not rocket science. What way is the water going to flow? It's going to flow that way. No. Now hold on, I'm going to cover this up for a second. Okay. Now, as soon as I remove my hand, there's going to be a flow from high to low, right? Pretty easy. Until it reaches an equilibrium. Now it doesn't get equal. Why won't it get equal? All right, because I put one of these on a block to illustrate exactly what I want to illustrate. Okay, now time out. Is the water moving? No. Is it possible though that there's a water molecule moving from here to there? Yeah, but if there is, then what must be happening? Then one has to be coming this way. Because water is constantly moving. There's a 100% guarantee that there is some water going that way right now. Or, you see the R? Should have used a different color. All right, or it's 100% likely that a reactant is forming a product. But if that's true and the water's not going up or down, then what must be happening to some product? It must be coming back towards a product. Now, this slide, is the amount of water equal on both sides? No. So it's at equilibrium, meaning the amounts are not changing, but there is an overall change, but we don't have the same amounts. Well, it's glued on, but if I did, then it would reach equilibrium and be equal. And that would just, it would reinforce an idea that kids have that's incorrect. So that's why we have that block. What's that? For now, we'll use these again in a couple days. If I want you to tell your partner, describe the flow of this water with the term forward or reverse reaction. So right now, what's happening? The forward or the reverse? The forward. Okay. It's forward because I have more reactants than products. But I can make it reverse. If I have more products than reactants, it will flow back the other direction. Where is this leaking from? I think my bottle has a crack in it. I didn't spill that much, I swear. I think it's got a crack. All right. It's okay. Now I got to find another kid that needs to pass the class that might have access to milk tubing. Oh, there is one. All right, well, we can visit about that. Where did it, oh, what the, who broke it? It has tape on it. Goddard? That man. Okay. There might be some glass down there from yesterday. Okay, that is a reversible reaction at equilibrium. I gotta hurry. The equilibrium position of a reaction is given by the relative concentration. Oh, that's a lot of words or a lot of letters for a small blank. Hey, Jason, welcome. If you tripped me with your leg, I'd feel bad, even if you did it on purpose. All right. Him. All right. Now, a chemical equilibrium position can be changed by applying a stress to either side of the equation. And we'll learn about this a lot in the next couple days. Once the stress is relieved, a new equilibrium position is reached where the forward and reverse reaction rates are once again equal to each other. What do we call it when the forward and reverse rates are equal to each other? Equilibrium. That says equilibrium. All right. No. Okay. I like it. The French chemist Henri Le Chatelier studied the changes in a system that result from changing the conditions of that system. He proposed Le Chatelier's principle, which is a matching term. And the easy way to remember this one to me is look for the word stress. So think about this. If you had to spell Le Chatelier on a spelling test, you'd be stressed. At least I would. So he proposed Le Chatelier's principle. If a stress is applied to a system in a dynamic equilibrium, the system changes to relieve the stress. That's like the dumbest thing ever. Like, hey, if you as a human get stressed, you're going to do something to relieve that stress. All right. Hey, why don't you guys get out of my room? Oh, we finished a slide presentation in one day. Of course, we didn't do the lab. This is my Pokemon I just drew.
I told them the highest bidder to have one. I'll take a nickel. No more and no less.
You guys are great. Adios, my friend. Have a good one. Goodbye, my friends. Goodbye, my friend.
Set Bob right there. Hey,
You-
Bob.
You want to take him throughout the day?
I was thinking about it, but Bob deserves to be where he belongs.
Okay, well, he'll be waiting for you tomorrow. Adios.